Okay, sure. Let's get to it. Yeah, so I gave a terribly inadequate description of how you can get a discrete sparse Fourier transform result from the methods that I just sort of briefly outlined on how to turn these compressive sensing sublinear time compressive sensing results into sparse Fourier transforms. Let me give you a theorem that you can find somewhere so that you see how well it performs if you're doing a discrete Fourier transform, and it'll be pertinent directly in a second. So let's do it. So here we go. So let's go ahead. Right, you can choose the size of, or take the size of your vector that you want to approximate the discrete Fourier transform of. It's going to be some integer. And you get to choose your sparsity. Right, some integer less than n, at least 2. And you're going to have some parameter r that has to do with your unequally spaced FFT techniques. So this Gaussian that you create, that you're going to convolve with things and sample from, sort of implicit in the paper. Right, and then you have a vector, I'll call f, of complex numbers of length n. Right, and you want to approximate its discrete Fourier transform. So all you can do are look at vector entries. You can't sample any function immediately anyways, anywhere you want. Okay, so there exists an algorithm, which is what we are just talking about so far, the last few lectures, plus some additional inputs from this unequally spaced FFT literature. So there exists an algorithm that will always return a vector v that's a good approximation to the discrete Fourier transform of f. Okay, so what does that mean explicitly? So the discrete Fourier transform of f, so this is a DFT matrix times f, right? The appropriate size, minus what this algorithm spits out, is going to be better than some absolute constant that you can bound. I think you can say it's something like always less than 198 or something if you do a not so great job of bounding it. I specialize in not so great job, right? Best S term approximation guarantee of your Fourier coefficients over the square root of s. So what you sort of want, plus the square root of s times the infinity norm of your set of samples times n to the minus r. Okay, so this is your error bound. So you can choose r to be moderately large, and you'll kill off, unless you have some really weird set of function samples you're working with. This is effectively 0, right, for a moderate choice of r.
Mark, sorry. So you're not dealing with noisy samples just for the sake of notational convenience, but it can be done.
It can be done with noisy samples, yeah, as well. So, but it's bad enough the way it is, right? So you can do this deterministically and always succeed in a runtime that scales like at sparsity squared, this r factor to the 3/2 power. That involves your sort of Gaussians that you're convolving with that you construct. Log 11 over 2 halves n time, if you want to give a rough bound on the power of your logs. So this will always work, right? It's deterministic, but you can make this faster if you don't want a quadratic in S runtime. So if satisfying the same error guarantee here with high probability is good enough. At least 1 minus p suffices. And you can do this by subsampling your grids that you use, effectively taking a smaller number of SFTs and doing a pared down version of the sublinear time reconstruction, compressive sensing reconstruction algorithm we've talked about. You'll have a Monte Carlo result as a variant as a result, meaning it fails with some small probability. But with high probability, it'll satisfy the same guarantee, and it'll run with the number of samples and the runtime that's just linear in S, same factor of R, log to the 9/2 n times log of n over p. So difference here. You have to take one of your log factors and make it n over p instead of n, and then you're fine. All right. Good. Yep.
When you say there is an algorithm such that specifically one of the algorithms that we learned the other session, or you mean
it is the algorithm from yesterday. I just so you could say there exists an algorithm, and it's the algorithm from yesterday with potentially some subsampling of the, and that, what does that mean? That also means you have to choose your P's and choose your Q's in a way that sort of makes sense. In the code that Craig is advertising on in the chat on Zoom, by the way, there are automated ways of choosing them. You don't have to choose them in the code. You just enter a sparsity and an n. And then there are fairly intelligent choices of primes and stuff that all happen in the background, and you can, so I believe the code is fairly user-friendly. You don't have to worry about all these details if you don't want to. Yep, so that's what I mean by exists. So it's exactly the method from yesterday. Plus this sort of quick way of computing those matrices times the Fourier coefficients by taking FFTs and blah, blah, blah. And the unequally spaced FFT techniques here that are sort of letting you take the samples you have available to you and get the ones that we just discussed in the last hour. So all of that stuff is the algorithm that exists, but it's laid out fairly explicitly in, for example, so if you want to see exactly a constructive version, so there's Murray, Zhang, and other authors. These are my some students of mine. It's a new class of fully discrete sparse Fourier transform methods, faster, blah, 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 right? Okay. Journal of Fourier Analysis. From 2019, I think. And there's a nice implementation also associated with that paper that's, I think Craig has improved in what he's talking about. Okay, so this theorem is proven in there and all the details are sort of gone through. Good, let me see. Yes, all right, so next thing. You might have a function of one variable, especially in signal processing type contrived contexts, because people can make their own functions that they need to sample in signal processing problems pretty easily, right? But you might have a function of one variable where you have a really huge value of n, sort of like a giant bandwidth, misusing terminology a bit there, where you have sparsity, maybe corresponding to a signal that somebody's hidden somewhere by modulating, using some modulation hopping scheme or something like that. So maybe this stuff has some value in those situations, but it's much easier to imagine that for functions of many variables where your space of Fourier basis functions grows exponentially with the dimension, that you can have a really huge dimension that you just can't handle, and you really want to do a sparse approximation there. So that's what we're going to talk about next. So what we're now going to do is assume that you believe that this proof is correct, and we have this algorithm, which is all the layers of stuff we've discussed. And we are going to use this as a black box to do function approximation for functions of many variables by finding good S-term approximations to their Fourier coefficients. So that's what we'll sort of talk about next. All right. Okay, so let's begin that process. So let's extend SFTs to functions of many variables. And we'll talk about some of the tricks you can use to do that, and sort of give you one reduction at least that lets that happen. All right, good. So, and I am going to talk about rank 1 lattice stuff here. It's going to be the easy trick of reducing to the problem of a one-dimensional function from a function of many variables. If you want to read more about rank 1 lattices, you can perhaps look at some papers of Lutz Kammerer if you want, or look at chapter 8 of numerical Fourier analysis. By Daniel Potts and some other folks. So it's a good place you can look for this stuff. Also, the unequally spaced FFT business that's involved in the proof here is sort of related things are reviewed in that book and other chapters. So it's sort of a nice reference for these types of things. Okay, so let's set up this problem. So we have a multivariate trigonometric polynomial. So a multivariate trig polynomial. Okay, so it's going to be a function from 0 to 2 pi. I'll use, I guess, little d. The complex numbers. And right, so that means I can write it in the following form. It's going to have some index set for its Fourier coefficients that are non-zero. I'll call it I for index because I'm not very creative. It's going to have, again, sort of vectors of length b, integer vectors telling us what the important frequencies are. E to the k dot x. X is our sampling value, right? And I can be any kind of arbitrary index set you want. I'll just stuff it into a really big, potentially large rectangle. So it's going to be a minus m to m to the d, some subset of that. Could be like a hyperbolic cross, could be some weird lower set. I don't really care. It's something. That's something in there. All right. Good. All right. So in order to build up the sort of rank 1 lattice method, I'm going to take a particular type of evaluation point that I want to stuff into my function. That's going to immediately simplify it. So let me go ahead and choose some value q that I'm eventually going to make a prime again. I'm sorry, but primes are just nice. There's a reason why people like them. So I'm going to take a sufficiently large prime, and I'm going to take my j sample to be j times 2 pi over q. And I'm going to multiply those values times some integer vector z. And I'm gonna mod every entry of Z out by Q. So this is a component-wise mod. And I want to point out that Z has integer values, right? So we're taking a set of integers and then we're modding it out by Q. Okay. So if you think about what this does, and then I'm going to take this, I'm going to let Z vary from 0 to Q minus 1. Right? Yep.
Excuse me, I just wonder, real applications, do we know that the frequencies that we're looking for, maybe this is a repeating question, but are we sure that the frequencies that we are looking for, they fall exactly onto the grids?
Oh, so if we're dealing with a trigonometric polynomial like this, then we're going to have integer frequencies. So that much we can be okay with. You can think of it as we're dealing with a multi-dimensional basis function, a product basis of one-dimensional Fourier bases. So this is going to be a spanning basis for your set of L2 functions that you care about, and so we're able to make these integers. Whether there will be a sparse approximation with respect to this basis is more what you have to worry about probably than anything else, but it'll be a basis and you'll be okay. Does that make sense? Yeah. Yep. So these guys will be integers, and if you take this thing for all possible sort of integer vectors, so all possible n to the d things, this will be a basis that you can work with for representing a function of d variables like this. Good. Any other questions about that type of stuff? Okay. So this is going to be a set of samples on this d-dimensional torus, right? Because I'm modding out component-wise here, what I'm really mod Q, what this is really doing is sort of the following, so that you have maybe some intuition for what these samples are doing to my sort of d-dimensional torus. So I've got my function defined on a donut, right? And effectively what I'm doing is Z is determining some sort of place that I start walking, a direction that I start walking in around the torus. And then I've got this sort of one-dimensional path that's sort of winding around this donut. And it's going to be a nice closed path because everything's periodic and I've sort of forced it to be. So I've got this path winding around the donut, and then I'm sampling values on this path. So that's what's happening here. I'm creating a one-dimensional path that winds around the donut, and then I'm sampling on the path. That's effectively how I've simplified the problem. And so you can sort of see right away that I've basically forced this thing into a one-dimensional box by deciding to maybe take samples of this type, and that's all we're going to do. Now it's a one-dimensional problem, I claim. Okay, so to see that it's now a one-dimensional problem, we can just substitute these guys into our definition of F. And so now I've got this jth sample. It's going to be equal to, I've got my indices and I, whatever it happens to be, Fourier coefficients. And when I plug this into my multidimensional Fourier basis, I'm going to get e to the 2 pi I inner product of k with z, whatever I've used to create my path around the donut, divided by q, right? So what have I done? Well, this looks now like a one-dimensional problem. I've got a new frequency, which is the inner product of these two guys, right? That's going to be the frequency associated with this Fourier coefficient is going to be this frequency, this one-dimensional value, which is just going to be some integer now. between 0 and q minus 1 inclusive. So that's sort of what I've done here. And so I need to choose my z and q intelligently, you would hope. Like if I choose q to be 1, this is clearly going to be really dumb. So I shouldn't do that, or 2. It's not going to work terribly well. So what I need in order for this to work is a good choice of z and q. So, and that will correspond to what's known as a reconstructing rank 1 lattice. Which there is a large literature for, or whatever set I happen to think my function has a good S-term approximation in. So this is a choice of integer q, and I'll take it to be a prime. To make my life easier, probably yours as well. And also a z that's going to sort of tell me how to walk around. And because I'm component-wise modding out by q, I can just make it in the set bracket q to the d from the get-go. And I want to choose these things so that z inner product x is not congruent to z inner product y mod q for all x and y in my set, my index set I, that are not equal to one another. Right? Very natural idea that's quite similar to all of the stuff that we were just doing in the one-dimensional setting, right? We effectively want z to hash any two things in I to a different place. That's all that's happening. So we've got like a number theoretic hashing going on, and that's all that's going on here. So in the spirit of my FM sort of mapping columns to numbers and stuff like that, maybe I have something a little similar here. So this induces some map H depending on z and q as parameters. It's going to map I, my index set, to let's say IZQ, which is going to be just the inner product of everything in I with z mod q. Right. This is going to be a subset of q. And we just want this map to be 1-to-1. And I should be invertible. So we've restricted the range enough. So this thing should be invertible, and then we're happy, right? So as long as this is invertible, it's the same thing as this, right? I have like a hash function that takes me from these vector coefficients of my supporting Fourier basis down to some integers in an invertible way. All right. So now working, I can rewrite this as a very obviously one-dimensional sort of problem using this sort of function, right? That I have here. Just do that. So f, these function samples that I have access to, the jth function sample is going to be equal to the sum over all the frequencies in this IZQ set. I can read, because it's if this is a reconstructing lattice, this is going to be a bijection, so I can call the Fourier coefficient omega. That's going to correspond to some inner product of its multidimensional support with z mod q. And this is going to be 2 pi I omega j divided by q. And this is a one-dimensional, now a totally clear one-dimensional FFT problem. So we take samples of this and figure out Fourier coefficients of this. Not only that, but right, like if the original Fourier coefficients are sparse, then these are going to be sparse because they're mapped 1-to-1 to these integers. So it preserves sparsity in the multidimensional Fourier basis. So we have a sparse one-dimensional FFT problem. And so we can use our one-dimensional sparse Fourier transform algorithm on this function. Basically taking those lattice samples, run our 1D FFT problem on it, we get our answer. So if our original function is S sparse or approximately S sparse, then this 1D version is also going to be approximately S sparse. And so we can recover with a 1D sparse Fourier transform. Right? It's pretty much that simple, sort of a black box sort of technique, with one caveat. So the output of everything that we've talked about so far, once we take this transform version of our function of many variable samples and run our one-dimensional method, we're going to get output that looks like this. So I'm going to have this function h, which depends on q and z. I guess I should put z first, maybe. At whatever multi-index for our Fourier basis has some non-zero Fourier coefficient. There are going to be, I'll call it K sub L, there are going to be S of these, so L will vary from 1 to S. I'll have F hat KL, or L equals 1 to 2S in general, or whatever. Maybe we want to take a few more. We have a little bit of freedom. All right. So this is the sort of output that my one-dimensional sparse Fourier transform is going to give me. It's going to give me something that's in Q, and then it's going to give me the correct Fourier coefficient, or at least a good approximation if it's truly S sparse. The problem is this Fourier coefficient value is associated with some like fake hashed version of my frequency, my true multidimensional Fourier coefficient, and I need to figure out what the Fourier coefficient is in the multidimensional setting, right? This is an element of Q. I haven't learned anything about the true multidimensional function from this yet. So in order to do this, we have to invert this sort of rank 1 lattice hashing function. And then we'll finally have whatever K we need in order to actually pair with this Fourier coefficient to create our good sparse trigonometric approximation. So there is one more component that we have to think about. But it's not too bad. So let me tell you how to do that. Or at least tell you a few different options you have. Okay, so now to complete the sparse approximation for a multidimensional function. Point is, we need to invert this map depending on Z and Q. Okay, so there are a couple different ways of doing this. So first of all, if you assume absolutely nothing about your index set where you have the good sparse approximation, so you take it to be the biggest possible. So I is just equal to this giant rectangular set of frequencies, and you're looking for the best S-sparse approximation in this whole thing, okay? There are H constructions that can be inverted in sublinear time, like log m time times d sort of type time. And these are sort of constructed using something very analogous to these K-alpha coherent constructions using multiple primes. They're a little bit different than the rank 1 lattice definition I gave, and that you want to mod out by a different prime in each variable. And then, but if you do that, you can use the Chinese remainder theorem sort of stuff again to reconstruct this sort of inner product map and tell you where this guy came from. So that's something that Martin Strauss, Anna Gilbert, and some of their collaborators came up with in one of the earlier SFT papers. It's also also talked about in this Acha paper of mine from 2013 that I referenced before. So you can do that, right? But then you have to use the full potato here for I, and maybe you don't want to do that. So really dumb thing you can do, if I is arbitrary and you're going to use it a lot, you could just compute this map and store it and then use a lookup table, right? If I is not too huge, that's an option. And so you can store a good HZQ inverse for I somewhere. Okay, that's less interesting for me because I sort of want to think about cases where I may vary from function to function, and this is what you need if you want good for each guarantees. So else, if I is huge, too big to store ever, huge, arbitrary, and can vary from function to function, then you can ask my graduate student Craig Gross how to do it. Okay, so he has a paper about how to do exactly this type of thing. So you can use specialized techniques to do this. All right, so, and if you want to see where those techniques exist in written out form, and also I should say the one-dimensional discrete sparse Fourier transform results that let you have noise on the samples are also in this paper. If you want to see what those look like, the non-simplified version. You can see it in Craig's paper. There are two sort of strategies for doing this for arbitrary I and sublinear time and the only problem is that you have to do several one-dimensional rank 1 lattice SFTs in order to get the information to rapidly invert this multiple rank 1 lattice thing. So Craig Gross, self, Kammerer, Volkmer, SFTs on rank 1 lattices. And this is in sampling theory, signal processing, and data analysis. From early this year, I guess it just appeared. Okay, and so the price you pay are you need some additional samples to pull this off for arbitrary I quickly. And what you end up doing is you have run times that are something like E plus one-dimensional sparse Fourier transforms that you have to run on different modifications of rank 1 lattices. So you have something like D plus 1 times the runtime of a 1D sparse Fourier transform. And these things are pretty parallelizable. So if you want to, you can do all of these sparse Fourier transforms and the little SFTs in each one of those all in parallel if you have access to your samples laid out nicely. And so there are nice things you can do like that. Both the linear and S randomized methods and the deterministic methods are sort of generalized to be able to do this in that paper. Okay, so good. How much time do I have left?
20
minutes?
25 minutes.
Okay, so let me give a slightly less known way of very easily constructing a rank 1 lattice. That's the last thing I'll do and sort of give a little proof. Yep.
You said in one that there are H constructions that can be inverted. What was H?
Yes, this is, I didn't want to call it HZQ because the Z is a little bit different than the way we defined it here, and it actually depends on multiple values of Q. But it's one of these types of functions.
Okay.
Associated with a lattice that isn't quite a rank 1 lattice, but still it's morally the same thing. Or maybe immorally the same thing. Yeah, so that's what I meant. Some very similar type of map from index vectors of integers to integers that you can then sort of invert quickly and do one-dimensional FFTs to figure out where things map back and forth really fast. All right, good. Other questions before I talk about rank 1 lattices a little bit? Yes.
Kind of a high-level question. So in the dimensions, we use the rank 1 lattice. So was this initially done like, and let's say if you have a low dimensional problem, say dimension 2 or 3, is it better to just try to recast this as a 1D problem where you can genuinely tackle that?
In 2D, you should probably just do a 2D FFT. You'll see how it depends on how Q scales, right? Because you have to do a Q dimensional, you have to do a size Q one-dimensional FFT. And I very cleverly not told you how big Q is yet. So it turns out that in like 3 dimensions and bigger, it probably is pretty good to use a rank 1 lattice type approach, but in 2 dimensions, you probably should just do a 2-dimensional FFT, something like that.
And then this begs the question now, let's say if you have a 2 or 3D way of handling the same technique, can you project a D-dimensional problem into a rank 2 problem, a 2D problem or similar? Is there any reason to do that? Like, or no?
For sparse FFT, maybe I would, let's say asymptotically in terms of asymptotic complexity bounds and error guarantees, probably not.
Okay.
for practical reasons in terms of real actual coding, maybe. There might be some good reason to do that depending on what two-dimensional FFT components you have that you can just call and that are super fast and optimized on, you know.
What I
some
mean, like if you
architecture.
project a very high dimensional problem, it's to say a rank 2 or rank 3 problem, then you will have to deal maybe with smaller primes, stuff like that, or like.
Yeah, that's true. Yeah, so that this tricks a little bit like that maybe will be used tomorrow in more generality, but not sort of going to the Fourier basis in particular.
Okay.
Yeah, there could be reasons to do that. I guess it would depend on more specifics of the problem. Good. Any other questions folks might have? Okay, so to talk about how to actually construct a rank 1 lattice and therefore construct this function, let's just give sort of an easy construction for a rank 1 lattice for an arbitrary I. That requires you actually to not even know what I is, which is my favorite type of rank 1 lattice or hashing, right? I just have to know a cardinality bound on I, and then I can win and come up with a lattice for it without having to even know what it is. So that's nice because maybe I don't know exactly that it's sitting in some hyperbolic cross sort of approximation space. Maybe I just have a feeling about the cardinality of whatever the weird set is. So here's theorem. So let's actually, maybe I'll put theorem on the next board. Because there was already a theorem there, so it feels right. And another reason why I like this is that it sort of actually can more directly be used to give you a much simpler multidimensional sparse FFT algorithm. If you think about it, that doesn't require you to do a rank 1 lattice method in order to get to a one-dimensional discrete FFT method, which is actually a combination of unequally spaced FFT methods plus some weird sublinear-time algorithm variant, which maps down to error correcting code stuff, right? That's quite a hierarchy. This sort of can get you there pretty directly if you use it in the right way, I think. So let's maybe finish with this. So I have some unknown subset of minus m to the d, and I have some probability that I want to succeed in reconstructing rank 1 lattice for this set. So go ahead and choose any prime that you like, although it should probably be the smallest admissible one. Q that's larger than the maximum of the cardinality of I squared divided by P and twice M. So whichever one happens to be bigger, plus 1, I guess, if you want to be formally correct. Okay, and then go ahead and choose Z, your lattice vector. Uniformly at random by selecting every entry from bracket Q, uniformly at random. Okay. So we're going to select each entry dependently and identically, uniformly at random. From Q, but we're not going to take 0 for obvious reasons, because that would be a dumb thing to do. That means effectively we'd be ignoring some dimension ultimately. So we're not going to take 0. Okay. If we do that, then this choice you've just randomly generated will form a reconstructing rank 1 lattice for I with probability at least 1 minus p. Okay. And just so what's the benefit of this over the giant literature of deterministic methods for selecting a deterministic rank 1 reconstructing lattice for a given set I? Here I don't even have to know what I is. So I just need an upper bound on its cardinality. Means in particular, as Craig pointed out in the meeting, that I can take I to be my best S term approximation for A coefficients. And then just generate a rank 1 lattice for that thing with a Q that isn't too big. And now I have a one-dimensional FFT I can solve and figure out what the answer is using sort of methods from his paper up here. So there's another reason to look at his paper. And then I don't even have to do sparse Fourier transforms. I can just do a small number of regular rank 1 lattice FFTs and sort of figure things out. But the probability of success will be worse than the best available. And there are downsides to doing that, but it sure is simple. So it's maybe nice to reference or sort of mention that you could do things that way. All right, so here's a proof of this. So using a standard sort of easy randomized construction type of approach, let's go ahead and fix some arbitrary vectors x and y from our index set I, right? Pick two that are different from one another. Right, and I'm going to think about these guys. And what we're going to do is basically show that the probability that they collide is small enough that it survives a union bound. And then we're done, right? So that's sort of what we always do in these sorts of situations, or can always do. So the probability that z, chosen randomly in this way, x is equal to z inner product y. So in other words, that I fail to be reconstructing for this particular pair, mod q. Right, that's going to be equal to the probability that z inner product x minus y is equal to 0 mod q. So I know how to manipulate inner products. Okay. All right. Okay, so z is not equal, or sorry, x is not equal to y, so they differ in at least one coordinate. So I can pick the entry, the first entry where they differ. There might be only one, in which case I'll pick the one where they differ, but they'll differ somewhere. So since x is not equal to y, that's y. They differ in a first entry j somewhere. Don't really care where it is. And q is larger than that difference can be because it's bigger than 2m. So that means that xi minus yj is not equal to 0 mod q. Okay. Where they differ in that first entry, and it's non-zero. So that means there is an inverse of this value, whatever it is, So this multiplicative inverse exists mod Q, it's Q prime. So that's going to be fine. We're doing arithmetic mod Q. All right, so now we're effectively done because I look at this probability that I want to think about. This is going to be equal to the probability that the jth entry of Z, which happens to hit that jth difference where things are non-zero, is equal to minus this inverse that exists times the sum of all the other entries of these ZLs times XLs minus YLs, whatever they happen to be, mod Q. Right? CJ is uniformly chosen from 0 to Q independently of all of this stuff, whatever it happens to be. So you can actually just say, choose these to be whatever you want or look at it, with them fixed. Point is, this probability is going to be less than 1 over Q minus 1 because the ZJs are uniform and independent of these guys. So by independence assumptions. And now we're done because Q is big enough to survive a union bound of all cardinality of I. Choose 2 combinations of X and Y. And so this basically automatically gives us our result. All right, so end of the story basically here. These rank 1 lattices, if you want the reconstructing rank 1 lattice, this is the optimal scaling. It's going to scale quadratically with whatever the set happens to be. That's the best that you can do, so you can prove that. There are deterministic algorithms, if you know I, that will construct near optimal rank 1 sampling lattice, but then you have to look over every entry of I. So if I is huge, that's going to take you a lot more time than you have if I is, really, really massive. In other words, if, for example, D is 100, you can't do that. So in that situation, you can randomly generate one and you'll win with good probability, especially if you make Q bigger, fairly large. And you can do that because remember in a sparse Fourier transform, you're going to have logarithmic dependence on the size of your one-dimensional FFT. So make Q bigger than you need it. I don't care. And you'll still be fine. And so that is sort of the end of the story that I had to discuss. I guess maybe I'm a little bit early finishing today, or maybe not, but I'm done anyways.
Okay, so that's great. So we have even more time for Q&A. I wrote down a couple of questions. Let's see first if anyone in the room has technical questions or big picture questions. Yeah.
So I guess this is more about like the numerical implementation of this kind of stuff. Are there sort of like numerical safeguards you have to implement in addition to like the algorithm, or does it kind of work like as described? Like
if you can understand the way I described it, that's pretty much the way it works. So in the way that I hope I was describing it, it should work without numerical safeguards, really. It's fairly robust. You generally, I guess, can't get these types of SS term approximation guarantees that let you have errors on the sampling, the samples that you give things if you have an algorithm that's like super unstable. You just won't be able to prove the result. So numerically, it works, pretty well.
So as a follow-up, like the MATLAB implementation that Craig was talking about, is it a fully MATLAB implementation, or do you have to build some kind of interface to do some low-level operation faster, like in C, something else, like.
I believe they're, Craig, are you there? My understanding is that there is potentially a low-level interface, but he's done it for you. So you just ask MATLAB to do stuff and it does it. Does that sound right, Craig? Did you already
Yeah.
leave?
I don't know. Can you hear me?
Yes.
Yeah. So it's mostly that has a pure MATLAB implementation in there. And then in addition, it wasn't me, it was Tony Volkmer who wrote a bunch of crazy C code that is interfaced if you want it to run faster.
Yep. Tony does do crazy C code well.
And so another follow-up question in this direction, so. I mean, a big issue seems to be, okay, maybe, I don't know, like numerically, the fact that you want to deal, maybe, okay, when your N is really large, then you're gonna need to deal with some large primes, I guess. So how much of, is this creating a problem, like computationally, is this tricky to handle, like how critical is that?
There are warehouses of large primes because cryptography applications use many huge primes, bigger than any prime you would ever want to actually use in this algorithm, probably, unless you're slightly nuts. So, right, like there,
Okay.
yeah, there are lists of the first like billion primes you can find online. Computing them from scratch takes time, but you don't have to. Like they're out there. The primes are out there. Right, so I myself have like, and actually MATLAB can generate the first X, primes where X is something fairly ridiculous quite quickly. They exactly for these sort of cryptography based reasons. So yeah. So you do need a list of primes, but you can store it in an array and then just use it while you're generating your matrices quite fast.
And at some point, you talked about aliasing and how we're taking advantage of that, but I couldn't follow where you were using and I didn't see actually.
Yeah. So the aliasing comes, so if you remember, we were taking these small SFTs.
Yeah.
For the one-dimensional stuff that we were talking about last hour. Maybe I'll. There we go. And I had things like this written down where I had a little Fourier transform matrix times some set of samples. Like this. Yep. So where does the aliasing come in? Well, I'm going to generate some frequencies between 0 and xj when I do this, some like discrete frequencies. But what are those discrete frequencies here? They're actually sums of all the Fourier coefficients that are congruent to each one of these j's mod xj going off to infinity if I'm taking pure function samples. So when I compute this discrete DFT matrix and I get some, I don't know what we want to call it, the jth entry of that, it's going to be equal to the true Fourier coefficients of this function times xj. It shouldn't be xj times whatever x. Dang, I overloaded j. Oh no. Let me use L. Apologies. There we go. That's correct. L entry of the j prime. So I'm going to end up summing all of these Fourier coefficients. But what is this? This is exactly the inner product of one of my rows from this K alpha coherent matrix, for example, with the Fourier coefficients of f. And aliasing hands me those measurements automatically. So this is usually considered a source of numerical error because it means you've chosen your grid to be too small, and so you have frequencies floating out in the ether, sort of telling you wrong information about the small Fourier coefficients and you're angry. But here I'm happy because I get to sum a whole bunch of Fourier coefficients that I don't want to actually resolve properly because I'm going to use that to figure out where the sparse Fourier coefficients live using this sparse Fourier transform structure.
So if my understanding is correct, actually aliasing is helping us to reduce the number of samples.
Yeah, yeah. By happening to correspond to this combinatorial compressive sensing stuff from yesterday.
Okay. Can you also suggest a paper where we can I can find more detail and
About
this?
this stuff. So I think that Acha 2013 paper by myself, you can look on my webpage. It's like improved approximation guarantees for sparse Fourier transforms or something like that. I think it's the only paper I published in Acha that year. You can find it on my webpage, or you can email me if you want, and I can send it to you, so you don't have to search for it. It's also good. Yep.
So at first, I see that you are assuming the function is an expansion of the trigonometric function. Right?
Yep. This is
So-
all Fourier stuff.
So what if we have noise in the function? I mean, if the algorithm still works.
You mean like noise on your, so if you mean noise in the function as in noise on your samples effectively that you
Yeah.
take from the function? Yeah, that as long as the noise isn't too extreme, it'll still work. So that's sort of similar to Simon's question, I guess, before. So you can get bounds that look like, for example, your error guarantees degrade like the infinity norm of the noise on any given sample. And then I suppose there are ways of fixing that so you can have a small number of highly contaminated samples, you know, but that's not actually published anywhere, but sort of know how to do that, I guess, in theory. So yeah, you can handle that. Then when you're doing more general function approximation, you take advantage of that because you sort of you approximate your infinite dimensional function by a trigonometric polynomial that's hopefully sparse. And then everything else, all the Fourier coefficients beyond your big N limit, you sort of dump into the noise. And then, you know, it's sort of the standard way of doing infinite dimensional function approximation using these sorts of things. And that works out okay.
So the online participants, do you have any burning questions? Could be to type in the chat or unmute yourself. Okay, so I wanted to ask if you could say a bit more on the example that you presented before going to the dimensions. Like, I was curious also historically, what was the kind of motivating problems that were out there when people started looking at this one-dimensional Fourier type approximation, Sublinear-Time?
I think two things. So first, there's sort of a class of, or a bunch of people in the theoretical computer science world that wonder about, is there an algorithm faster than the fast Fourier transform? Because there's nothing telling you that you can't do it in linear time. So theoretically, algorithmically, maybe there's something better than n log n time, or right. And so this is some way of sort of approaching that. So if it's sparse, so yes, so I can do better than even linear time. It's amazing, you know. So that's one reason why I think they were interested in that, because it's a fundamental algorithm, very influential from that side. But also in the signal processing universe, I guess there are somewhat contrived, but not too contrived examples of radar signals in the desert somewhere. You have you're being pinged by radar, so you have some small set of frequencies that are sort of over a giant range. And if you want to discern a Russian ping from an Italian ping, I guess there are certain equipment specifications that will chirp in different ways. So you want to quickly find the frequency set, figure out what the chirp rate is, and then maybe blow it up or not. So there are signal processing reasons to want to very rapidly identify like frequency support that people have also thought about a fair amount, and that was a motivating factor and may still be for all I know.
Okay. So if there's no further question, let's thank Mark again. We'll meet tomorrow, same time, 2 p.m. East time here or online. Thank you again, everyone, for attending, and Mark for the wonderful second day of mini course. We look forward to the third
Yep.
day.
The third day will be different than this. So if you hated this stuff, you can come back for something different.